Hello, this is Keith Donohue, and I'm recording a supplemental lecture for my experimental methods, that is my statistics class, Psych 440, 640, that I'm teaching at NDSU in the spring of 2016. So if you're watching this video, you're probably a student, or you're hopefully a student in my class, or if not, maybe you're just someone who's curious about these topics. Basically, the idea for this little supplemental lecture came to me, as so many of these ideas do, after I finished a regular lecture and realized that I hadn't really covered a couple ideas in a way that was maybe very clear or comprehensible, at least not as much so as I would have liked. I had been talking a couple weeks ago about the choice that we make of estimators when we are developing models using the kind of general linear model approach to model comparisons that we often do in the type of statistics that psychologists often use. So I wanted to go back to that topic and explore it at somewhat greater length. So the goal for right now is just to quickly review what I mean by models in case there's any confusion about that. I'll engage in a little bit of a digression on sample sizes and outliers because that's actually kind of important to estimating parameters. And then I'll talk a little bit about choices that we can make between different estimators of parameters, especially for central tendency. And I should say a lot of these ideas are ideas that I got from Judd McClelland and Ryan's excellent book, Data Analysis, a Model Comparison Approach. So don't want to take credit for that myself. I strongly recommend that people watching this video go find that book. It's very affordable. It's published by Routledge Press. It's good. I like it a lot. So when we talk about models, at least the type of models that we often use when doing statistical analyses, especially hypotheses testing in psychology, we're often talking about something that looks a little bit like this, the kind of familiar linear regression model where we have a set of predictor variables which have weights attached to them, which are used in some linear combination to predict an outcome variable. And what we're trying to do here is we're trying to use our sample data to estimate an effect in the population, or perhaps even a set of effects in the population. If we go down to a very simple model, it might look something like this, where each participant or each case in our data set is given the same predicted value. There are no other predictor variables which increase or decrease the value of this prediction. This is a flat line that's horizontal with respect to the x-axis. Now this value could be something like the mean for the outcome variable y. So everyone in the data set, if we know nothing else about them, we're just going to give them the prediction that they all have the value of the outcome variable that is equal to the sample mean. And we're using that to estimate a population mean. Again, this is a simple model. What we're trying to do is describe where most of our data are, both most of the data in the sense of the sample data, where is most of it located, and also we're trying to use that to estimate where most of the population data is. If I said I have a group of participants and they all have some measured level of neuroticism on a questionnaire, or they all have some measured level of heart rate using EKG, we might, or you might ask me, well, what's the average, or what's typical for people in your group? I guess I just kind of tipped my hand there because of course there are different estimators that we can use to describe the central tendency of an array of data. A common one, of course, is the mean, or the arithmetic average. And this is one that we're of course all familiar with. If I again have a sample of data and I say, well, yeah, I've got this outcome variable that I'm measuring, almost reflexively you might ask, well, what's the average for that group? What's the mean level for that group? So again, it's clear that we often use the mean when describing our sample data, and we often are interested in estimating the mean in the population, and this makes sense because it's useful usually to describe where most of the data kind of piles up. But there is a problem with the mean, or at least there sometimes is a problem with the mean, is in that it is influenced by the shape of the distribution of the data that we have. This is a familiar problem that you probably already know about, or maybe you encountered in a very early statistics class that you took, which is just simply that the mean is sensitive to outlying values in the distribution of data. So in this case, we have a pretty small set of data, and there's one high value of 10, which is outlying, at least with respect to most of the rest of the data, and it kind of pulls the mean upwards. You might just by eyeballing this histogram say, well, most of the data is located at about 3, but if you were to add up all those values and compute the average, the mean is 3.6. So that value of 3.6 isn't entirely wrong, it's just not perhaps the best estimator of where most of the data lies, where kind of the middle of the data is. In fact, a better estimator of that, or a better descriptor of that data in this sample would perhaps be the median, which stays at 3. And for what it's worth, the mode, the most frequently occurring value, is also 3. So perhaps the median and the mode are better descriptors of the center of this data set and better estimators of the center of the population distribution that this data was presumably drawn from. So anyway, the question that you might have, or the question I had when I was sort of thinking about this, is why is it the case that we don't use the median very often in the type of statistical tests which I'm most familiar with and probably you're most familiar with, things like t-tests and ANOVAs, regression equations. We're often using the mean, even though it seems there are situations in which we might not want to use the mean because of the influence of outlying variables. Why not then instead use the median? Wouldn't that avoid some of those problems? And by the way, it's rare that we use the mode in much of the tests that we do, just because in continuous data there often isn't a clear or single mode. So the mode's kind of a nice choice that we maybe quickly reject, but there's still this kind of question of why don't we use the median? Well, in a way it's a bad question, or at least the way I phrased it is a bad question, because there are some statistical tests which do use the median. Some so-called robust tests make use of the median. There are some non-parametric tests that use the median. These are tests which are designed often expressly to deal with situations in which data is non-symmetrical, especially when it's not normally distributed, when it's skewed or shifted to one side or the other. But again, most of the tests that perhaps I'm most familiar with and that you're most familiar with do in fact use the mean, and they're the tests that we're going to focus on most in this class. Why don't we use the median? Why not? Well, it has to do with the choice of estimator. Why do we choose the mean over the median for most of these types of analyses? The mean, the median, and for what it's worth, the mode are all estimators. They happen to be estimators of central tendency, and we can evaluate estimators in terms of 3 basic criteria, those being unbiasedness, consistency, and efficiency. And in just a few more slides, I want to talk about these 3 criteria and compare the mean and the median in terms of these 3 criteria to see why it is, or to find an answer to that question of why it is that we often prefer the mean to the median in the types of analyses that we do. But first, before I get there, I want to digress a little, as I said I would, to talk about outliers. Now, I've already introduced what outliers are, and probably you already are familiar with the idea of outliers. These are just values which are extreme within a data set. And they're interesting to us and they're troubling to us because they tend to make analyses that we're trying to do tricky. They tend to bias estimators, meaning that they tend to pull estimators away from the true parameter value that they are trying to estimate. So if you had a sample of data on, let's say, measured level of neuroticism among college students, but that sample had a number of extreme cases, perhaps people who are very neurotic, who might have frank psychopathology, those values are going to drag the sample mean higher probably than it should be for the sample, and will pull off that sample mean's ability to accurately reflect the population mean. You'll tend to overestimate what is the real population mean for neuroticism among all college students if you have a sample which contains a lot of outliers. So that's one problem. A related problem is that outliers can distort different sorts of analyses that we want to do. And I realize that's kind of a vague statement, but suffice it to say that analyses like t-tests and ANOVAs and regressions, because they use the mean, if you're giving those analyses inaccurate or biased information in terms of means, this can reduce the power that those tests have to detect real effects, and they can sometimes produce odd or spurious results, giving us an incorrect impression of what effects might exist out in the population. So outliers can make our analyses, can make our work tricky, and for that reason I think it's worth identifying them and interrogating them. And by interrogate, I just mean asking some questions like, is there a good reason that we have these outliers in our data set? And if there is a good reason, or if we can understand where they're coming from, does it make sense to remove them or perhaps replace them with other less extreme values? So let's see how this might work, or consider a little bit about how this might work. First, we'll begin with an assumption that whatever it is we're studying, in this case we could imagine it's level of neuroticism in a population of college students, we could imagine it's level of anxiety in a clinical population, whatever else, we're imagining that it is normally distributed in the population. You might ask, well, why are we doing this, or does this make sense to make this assumption? I'd say yes, or at least often yes. Many phenomena that we study in the social and behavioral sciences are just, we think, normally distributed in the population. Just lots of things in the natural world tend to be many cognitive abilities, many personality traits, many attitudes, etc., etc. So just beginning with an assumption that what the thing is that we're studying is normally distributed in the population is, for many cases, a perfectly reasonable and appropriate thing to assume. So if that's the case, how might we go about identifying in our sample values which are outlying? Well, one thing we can do is we can create visual representations of our data and try to just inspect them for outlying values. So we could make things like box plots or histograms of data, and if we assume that we're sampling from a population that's normally distributed, we can go look for values that fall outside of a range that we'd expect in that population. So if we see a value, like I just picked a point here that's about 3 standard deviations above the mean in the histograms, or also equivalently in the box plot, you can see that this value, whoever this person is quite a bit more extreme or large in the thing we're measuring, let's say neuroticism, than pretty much everyone else. It's not to say that there's not a good reason for that, but it certainly helps us find people who stand out from the rest, or find cases which are unusual with respect to the rest. A related idea would be, or a related thing we could do would be to compute z-scores for all the values of all the cases in our data set. So we could take each person's score on the variable that we're trying to predict, and we could subtract it from the mean and divide it by the standard deviation, giving us the familiar z-score for that person. And if we assume that we're sampling from a normally distributed population, we know that extreme values for z should be relatively rare. And a rule of thumb that's easy to remember would be less than about 5% of the cases in our sample should have z-scores that are greater than greater than positive 2 or less than negative 2. So greater than an absolute value of 2, and less than 1% of our cases should have z-scores that have a greater absolute value than 3. If we want to be a little bit more precise about this, we can say that 95% of the scores in our data set should fall between about negative 1.96 and positive 1.96. 99% of the scores should fall between negative 2.58 and positive 2.58, and just about all of them should fall between about negative 3.29 and positive 3.29. And these numbers are probably familiar to you, or you probably heard them before, or maybe know exactly where I'm getting them from. I'm getting them from the frequency distribution of the normal or bell-shaped curve. You can see here, if you look at the bottom line, the different z-scores, and then sort of transpose that to the top curve and the percentages reported there, you can see that most of the data falls within about 2 standard deviations up and down from the mean. So if I'm looking at my particular data set and I see 1 or 2 people who have z-scores that are +3 or +2, that may be okay. But if I see lots of people who have z-scores that are extreme in the positive or negative direction, that might make me really start to worry that I have a lot of outliers, or that there's just some other problem going on in my data set. Now it's important to note here that, and I've said this a couple times, we're assuming that we're sampling from a normally distributed population. And also we're assuming, or I haven't really made this clear, but it's important, that we're drawing fairly large and ideally randomly selected samples from this population. If those two things are true, if that assumption holds, and if we are in fact drawing large samples randomly from this population, then it's quite easy or quite straightforward to interpret values which have large cases which have large z-scores or very, very small z-scores relative to the mean as being outliers. And doesn't necessarily say why they're outliers, but it tells us something that's important, or at least something important is probably going on there. If these two points don't hold, if the assumption doesn't hold, and if we're not in fact drawing large samples from a population, it can be hard to tell. You could imagine in an extreme case, if I had a very small sample, like 5 people in the data set, and I hadn't randomly sampled from the population, it might be really hard to interpret the existence of a very extreme z-score. Is this person extreme relative to the rest of the data in the sample? Sure, but what does that tell me about whether he or she is extreme relative to the rest of the data that's in the whole population? I just can't tell. And this is a reason, and there are many others, why it's important to use large samples in our research, and ideally random samples, although and this could be its own whole separate supplemental lecture. We of course seldom, if ever, do real random sampling from a population. We might at best approach some sort of representative sampling from a population, but at the very least we need large samples. Small samples are just inherently difficult to work with, or can lead us to all sorts of mistakes or flawed inferences about population. So for this reason, for other reasons that I'll get to, and for reasons that I won't get to, at least not right now, avoid small samples. Okay, so we've identified some outliers, or at least I've briefly talked about some ways that you could, in principle, identify outliers. Now let's get on to interrogating them. And interrogating, as I said before, is just my way of saying we should ask the question, why are the values for our putative outliers so extreme? Now there may be good reasons why values in your data set are extremely large or extremely small with respect to most of the rest of the data. There could be problems with measurement. Your equipment might have failed that day. Your computers were installing updates and were working slowly, or equipment doesn't necessarily have to be computers. It could be equipment in the sense of there was poor photocopying on your questionnaires and the instructions were not clearly written, or someone in your sample was being rushed by your research assistants and he or she didn't have time to carefully read or respond to the questionnaires that you presented. So there could be equipment problems, there could be data recording errors. You yourself or your research assistants might have accidentally keyed in an incorrect value, making that particular case look extreme on some sort of measure that you're trying to record. There could also be problems with your sampling, and these may be a little bit more subtle or difficult to identify, but it could be the case that one or more of your participants really isn't in the population that you're interested in sampling. So I've used this kind of vague example already of sampling from the population of all college students and measuring something like neuroticism. It's conceivable that someone was recruited into your study who has a very extreme level of neuroticism because he or she is diagnosably mentally ill, perhaps they have very severe depression, maybe they're not even really a college student, or they're not a college student in the way that you're conceiving of the population of college students. They essentially wandered in, figuratively or literally, into your data set, but they shouldn't be there. And this can actually happen a lot in research settings. You might accidentally recruit someone who really shouldn't be in your study because he or she isn't really a focus or part of the population that you say you're studying. So if these types of reasons exist for your extreme data, it may make sense to remove the values that are offending or outlying, or to replace them with some of the other less extreme values. And I think it's important as a researcher to be very honest with yourself about this. It's not just enough to find outliers, but it's important to ask, why are they outliers? You should keep good notes so that you can record if on a particular day the computers seem to have trouble, and that was the day that person number 12 in your data set was being recorded, and down the line when you're actually looking at the data you see that yes, person number 12, she's the one who seemed to have these really weird scores on that computer task that you were measuring that day. It's important to have good records so that you can, as I've said, interrogate unusual, perhaps extreme or outlying values. Now, unfortunately, there can be bad reasons, or at least one bad reason I can think of, to remove or change outlying values. And that might be that if you keep the value in your data set, it makes your analyses non-significant. So using our traditional criterion, P is greater than 0.05 when you include person number 12 in the data set, but when you remove her, all of a sudden P is less than 0.05. And it can be very, very tempting for a researcher, especially if you've invested a lot of time and effort in your study, to say, oh gosh, I think I'll get rid of person number 12. Yeah, her data looked kind of weird. Yeah, she probably wasn't paying very much attention when she filled out the questionnaire. You can talk yourself into this, and I would argue that you shouldn't, although it's a temptation I'm sure we all, if we're being honest with ourselves, feel from time to time. You sometimes hear statisticians or people who are into data analysis use phrases like, the goal is to fit the model to the data, not fit the data to the model. And what they usually mean by that is we should construct a model, a regression equation, a set of analyses that reflect the data we have, not prune back or trim back the data so as to give us a model which seems clean and elegant and is significant with respect to P less than 0.05 in our null hypothesis significance testing. So that's a bad reason. People do it, I'm sure. We're all tempted to do it, I suspect, but I would argue it's a bad reason. And there are probably all sorts of other just bad reasons. Like if you don't have a good reason or a good explanation as to why a value is an outlier, then maybe it's not good enough. If you have a good reason to explain why they're an outlier, fine. If you don't, then be honest with yourself, you don't. And under these type of situations, I would argue it doesn't make sense to remove or change values of data that you have. You could, it's your data, but I would encourage you not to, because I think it's a very slippery slope to do this. You can be one of these people who will claim that they found a particular effect, but if you press them on it, they'll say, oh, well, yeah, I had to trim away 12, 15, 20% of my data to get the effect to, quote, be significant. And that is suspicious for all sorts of reasons. Anyway, with that digression accomplished, if you want to call it that, let's move back to talking about our estimators. And specifically what I want to do is simulate, or take advantage of a simulation that I found online, simulate a bunch of sampling distributions for the mean and the median. Once we've done this, we can describe their differences in terms of bias and consistency and efficiency. And by way of a quick review, a sampling distribution is just that. It's a distribution of statistics, in this case the average or the mean in this picture, drawn from successive samples. So you might do one study, you find the average level of neuroticism in your group of people. You could, in principle, just repeatedly, an infinite number of times, gather samples from that same population, ideally randomly sampling that population, although of course we almost never do that. And each time you record the average or the mean, and you take all those means and you put them together in the distribution, and you would have a sampling distribution for the mean. Now, for a long time, or at least for a few days or weeks spread out over different semesters, I've tried to figure out a way to, in Excel, develop a little sampling program myself. I probably don't have the computer programming chops to do that. Thankfully, someone online, and I've put the URL here, developed a kind of a simple web-based simulation for simulating sampling distributions for different estimates. And so what you can do here is you can start, as I have, with a normally distributed population of data, and I can simulate different sample sizes, either 5 times or 10,000 times or 100,000 times, to look at differences in some of these criteria. So let's start with unbiasedness. So we'd like an estimator to be unbiased in the sense that we'd like it to accurately indicate where the real population value for that parameter is. So if we're talking about the sample mean, we'd like the sample mean to point, if you will, to the real population mean. So using this little online tool, what I've done here is I've taken sample size 5, which is of course ridiculously small, and I've sampled a little over 1,000, I'm sorry, a little over 10,000, 10,005, because I kind of clicked the 5 sample and then the 10,000 sample. 10,005 samples of data. In the first set of 10,005, I had the computer compute the means, and in the second sample of 10,005, I had them compute the medians. Or actually, it's the same sample of 10,005. It's just one simultaneously. It was computing the mean and plotting them in one group, and computing the median, plotting them in another. And you can see here, I hope that what you get is a distribution that's kind of a mound. It looks sort of vaguely bell-shaped, and it looks sort of like the population distribution above it on the picture. And what's important here, I hope to notice, is that the center of these sampling distributions for the mean and for the median are lined up, and they're lined up beneath the center of the population distribution. So what this tells us is that the mean and the median, at least in the simulations that I've run, and this is generally true and can be mathematically demonstrated, they're unbiased estimators. The center of their sampling distributions points to the center of the population distribution. Now let's consider consistency. We like our estimates to be consistent in the sense that we'd like them to get better. I'll talk about what I mean by better in a second. We'd like them to get better as we increase the size of the samples that we're working with here. So here is a situation like before. In fact, it's exactly the same as before, where I've got 10,005 samples of n equals 5. I've computed the mean, or had the computer program compute the mean and the median. Now I'm doing the same thing, except this time I've drawn 10,000, so slightly less than 10,005, but that doesn't make a difference. Almost as many samples, except this time they're all sample size 20. You can see over here on the side it says n equals 20. And hopefully what you noticed is that the sampling distributions just got quite a bit narrower when I clicked from the one picture to another. And what this means is that in a sense the sampling distributions are getting better at estimating the population distribution, or at least the parameter that we care about, the center of the population distribution. They're becoming more narrow and focused, if you will, on the center of where the population is. So the mean and median are both consistent estimators. Their sampling distributions get narrower as the sample size increases. By the way, this is another reason to use large sample sizes. If you use large sample sizes, you get more efficient, or, well, we'll talk about efficiency in a second, more consistent estimation of the parameter that you're interested in. And at the risk of launching, or without launching into a whole other digression, this is because of the central limit theorem, which just says that when we create an aggregate of a number of calculations from successive samples, the larger the sample sizes for those calculations, the more the distribution of resulting calculations will tend to resemble a normal or Gaussian curve. And it's probably could be put a little bit more elegantly than I just put it, but the bottom line is that larger sample sizes, the closer the sampling distribution gets to the normal curve. And you can kind of see that here. So this is an image where I've got sample size 5. I believe this is like 10,000 or 100,000 samples conducted and formed into a distribution. the the sampling distribution on the left looks kind of normally distributed, and you can see that the mean is 4.64. Standard deviation is fairly wide, it's 1.25, 1.29. If we look at sample size 50 for the same number of samples, except this time each one contains 50 participants or 50 cases, that curve, the one on the right, looks a lot more like a normal curve. It's because of the scaling of these two images, it looks like the one on the right is much more peaked, but really the one on the right is much more consistent with a normal curve than the one on the left. And what's important is the mean is 4.5, which happens to be the real population value for the mean in this simulation. And of course the standard deviation, or the sampling, the standard error as we might call it for a sampling distribution, is much smaller. So the final criterion is efficiency, and the way we can think of efficiency is how precise is the estimation. If each estimation is a dart thrown at a dartboard, how tightly clustered are those darts? And we saw that in general, as we increase sample size, the estimators like means and medians tend to get more narrow, more focused, more consistent. We can also see, if we look at large numbers of samples, how the standard deviation of the sampling distributions differ. So here we've got a sample of 10,000, sample size 20 means and medians, and it might not be really obvious, so I've tried to highlight it here, but the standard deviation, or the standard error, because we're talking about sampling distribution, is slightly narrower for the mean than it is for the median. It's not a big difference, but it is a difference, and we'd see even more if we had larger size samples or larger numbers of samplings, or larger numbers of samples drawn, instead of 10,000, 100,000, or a million, or so on. So the mean is more efficient, at least slightly more efficient than the median. Its sampling distribution is slightly narrower, or the standard error, that is to say the standard deviation of the sampling distribution, is slightly smaller than is the case in the median. You might be asking yourself, why is a narrow sampling distribution good? Well, we could probably answer that question in a couple of different ways, but perhaps the simplest way to think about it is that a narrow sampling distribution gives us more power to detect significant effects. Test statistics have a lower probability within a given sampling distribution. Test statistics associated with a non-null effect, I guess is more precisely said, have a lower probability in a narrow sampling distribution than they do in a wide sampling distribution. So you can kind of see that here, though again, because of the scaling of these simulations, it's not super obvious, but I've created kind of a generic test statistic. I'm calling it T, not necessarily to say it's a T statistic, just it's any old test statistic, and let's say it's revealing a non-null effect. There really is a difference between two groups or whatever. You can see that that value is about the same distance from the middle of the sampling distribution for the mean as it is from the middle of the sampling distribution for the median, but there's a taller column of values over it in the sampling distribution from the median than there is in the sampling distribution of the mean. Essentially, that test statistic occurs more frequently in a null distribution for the median than it does in a null distribution for the mean. So, if you computed that test statistic, and let's say you could sort of post-fact decide to subject it to analysis in either a null distribution for the mean versus a null distribution for the median, you might well find that it's significant when you think about it with respect to the means, but not with respect to the medians. That's a little bit weird to say it that way, I suppose, because it's not like you would decide that after the fact, but maybe another way to put this is a larger difference or a bigger effect is necessary to, quote, show up, unquote, as significant if you're working with medians than it is if you're working with means. Okay, so here's a quick review. What have we learned so far? Well, there are different ways of estimating parameters. Here we've really been focusing on just parameters that are the center or the central tendency of the population distribution. So if we wanted to talk about the center of a population or the centers of groups in the population, we have choices: the mean, the median, the mode. Like I said earlier, we sort of dismiss the mode almost immediately because often it's just not useful to us. But if we're thinking about the mean versus the median, we usually prefer the mean to the median because it's unbiased and consistent and slightly, at least slightly, and sometimes more than slightly, more efficient. But to be clear, this is only when we remove outliers, if that's possible, and when we're using large samples. And what constitutes a large sample is not entirely clear. It depends on different factors. But to be clear, we're talking about samples of 20 or 30 or maybe even much more than that, depending on the type of calculation we're trying to do. Larger samples, for all sorts of reasons, better than smaller samples. So as I finish up this little supplemental lecture, I want to raise a complicated question or complicated set of questions and maybe sort of answer them, though probably not as best as I can, and perhaps I'll do another supplemental lecture down the line. I said earlier that we're going to assume, for the purpose of that previous example, that the population distribution of the thing we're studying is normal. So things like cognitive abilities, some of them at least, personality traits, qualities of emotionality, many of these things seem to be normally distributed in the population. But of course, there are some things that aren't normally distributed, and a really good example of this is reaction time. Very often, if you're studying something like people's reaction time to a particular type of sort of emotional prime, or a particular type of sort of cognitive prime, or emotional stimulus, whatever, people have to sort of press a button if they see it, not press a button if they don't, or vice versa. What you get is a distribution of values that don't look particularly normally distributed. In fact, the distributions you see might look something like this. This is called an ex-Gaussian distribution. It looks a little bit like a normal or Gaussian distribution, but it tails out or skews to the right, to the positive direction, meaning that for the most part, people tend to react quickly to whatever the stimulus is. In this case, the center of the distribution is kind of around 400 milliseconds, but sometimes they respond much more slowly, stretching way out to like a full second out, or a second and a half out, or further on. Reaction times have been characterized as having this ex-Gaussian distribution, and an ex-Gaussian distribution, probability distribution, has three parameters that define it. There's mu, which is kind of like the mean, the center of that sort of major hump of the distribution. Sigma, which is kind of like the standard deviation, so how wide that sort of central hump is. So mu and sigma look a lot like mu and sigma look for the normal distribution. The difference is in the ex-Gaussian distribution, there's this third parameter, tau, which is kind of how taily or sort of stretched out that right tail is of the distribution. And what's tricky about analyses of reaction time data is that in principle, you could conduct analyses on any or all of these parameters. Instead of being just focused, as we were before, on the mean, or mu in this case, kind of the center of the distribution, you could say, well, under what circumstances does tau extend? Like, are there some stimuli in my study that tend to make people much slower, and that slowness shows up in the tail, but not so much in the major mass of the data? I'm not someone who uses reaction time data in my research, or at least in the research I used to do, so I can't speak too much to the particular theories that might lead you to make one set of predictions versus another. But suffice it to say that you could, if you had theories about the nature of the processes that underlie reaction time, predict any of these parameters, or predict effects that would occur in any of these parameters. The problem is, or a problem, and I'm not the only person to have thought of this. In fact, many people have written about this. I've tried to catch up on this literature in recent days. Most of the analyses that people do with things like reaction time are the kind of conventional analyses that are familiar to most psychologists, things like t-tests and ANOVAs and regressions and so on. The problem with that is when they're using these analyses, whether the researchers realize it or not, they're using means to examine effects. So is one group slower than another? Are people faster under one condition than they are under another condition? They're using mu as in the mean, not mu as in the ex-Gaussian mu. And that mean, that simple old mean that we're familiar with from the Gaussian or normal distribution, is not a great estimator of the center of the ex-Gaussian distribution. Things like the skew and the possible presence of outliers, especially high outliers stretched out into that tail. Also other problems that I haven't even addressed, like differences in variability between groups or between conditions, often end up in reducing the power of these analyses, that is, reducing the ability of these ANOVAs or t-tests or whatever to detect real effects that are there, and can sometimes lead to weird or spurious results, or, as I tried to indicate here, send you off on the road to disappointment with your analyses. Now, recognizing the mean is maybe only really useful if we're talking about populations that are normally distributed. Not always, but especially populations that are symmetrically distributed and especially normally distributed. What do we do in the case of reaction times which are not symmetrical and not normally distributed? Well, some analyses use medians to examine these effects. There is a literature out there that uses the median as a way of describing the center of a reaction time distribution, because that's a little bit closer to the middle of that hump and not so much pulled out towards the tail. There are also analyses which will use the interquartile range as a stand-in for the standard deviation, because it's a better indicator of the dispersion of that central hump of the reaction time distribution. It's interesting to note, and this is something I've read about fairly recently, that the median is a biased overestimator of the population distribution when the population distribution is skewed. So earlier on I said, oh, the median, it's an unbiased estimator. That's true when the population distribution is symmetrical. In fact, I didn't do this, but you can with that simulator that I linked to. You can make the population distribution skewed, and then you can actually see this yourself. If you try to create sampling distributions for the median, the center of that sampling distribution for the median is going to overestimate the center of the population distribution if that population distribution is skewed. Now, interestingly, this problem of overestimation is lessened if all the groups in your study have an equal number of trials. So if you had some people who saw one set of primes or stimuli and another group who saw another, provided that both of those groups went through the same number of reaction time trials in your study, it's not that big a deal because both groups are biased equally or roughly equally, and thus any biasing effect kind of is averaged out, which is a little bit of an awkward way of saying it, but you don't compound that bias or create a situation where the bias interacts with group, masquerading as an effect which isn't really there. So, you know, hint, hint, for all sorts of reasons that I haven't talked about, but probably will in future lectures, it's great to have balanced designs in which there are the same number of stimuli or trials for each of the groups that you're using, or each of the conditions that you're using, if it's a within subjects type of design. It's also interesting to note that this problem of bias, of overestimation, is much worse when sample size is small, or especially bad if sample size is small and uneven between your groups. Like one group had only 10 people in it and they saw a certain number of trials, and then the other group had 20 people in it. Those type of situations are terrible because then bias is a problem and it can interact, or it is, no, I shouldn't say interact, it is associated with one group as compared to another, and can lead us to all sorts of problems with seeing effects which maybe aren't there, false positives, or maybe missing effects which are there. So at this point in the supplemental lecture, it's probably seeming a bit repetitious, but this is yet another reason to use large sample sizes. Small sample sizes are really problematic, and I know I said that in previous lectures, including in a previous supplemental lecture for this very series that I recorded last week. So what do people do when they deal with reaction time analyses? Well, there are approaches which involve cutting out outlying values. You might sort of arbitrarily say that reaction times above a certain millisecond threshold are just not of interest to your analyses. Hopefully you have a good reason for choosing whatever threshold you choose. Some researchers, a lot of researchers, will use values like 2 or 3 standard deviations above the mean. These can be somewhat problematic because they're variability from one subject to another, but it's the same sort of idea. And to the extent that you remove high values out in that right tail, you reduce skew at least a little bit. A lot of researchers will transform data, so they'll take the inverse of reaction time, which is speed. Taking the inverse of a skewed data set or skewed distribution lessens the skew. Log transforming or square root transforming will have a similar effect. There are challenges associated with transformed data in terms of how to interpret results that you see, but that's a popular approach that people will do. And there are all sorts of what I'm calling advanced techniques, just because I don't understand them all that clearly, where you just try to estimate those separate ex-Gaussian parameters, or you do a process called Vincentizing, where you create different quartiles or quintiles of data and try to talk about effects which exist in each of them, which is in some respects similar. You're taking that sort of broad and kind of skewed distribution and you're hacking it up into pieces, and you're saying, all right, well, what's happening in the early element or in the middle element or the later element or so on. It's funny, I really should learn more about this, and perhaps I'll even do a supplemental lecture a little bit later on about how to deal with skewed data sets, and especially with reaction time data, because it's something I don't have a lot of experience in, but it's clearly kind of interesting. All right, so another review. What have we learned? Well, non-normal distributions are tricky. Population distributions, that is. They're tricky for all sorts of reasons, one of which is it's not entirely clear what we're focusing on, or it isn't as obvious. In the case of a normally distributed population of data, it's reasonable to say let's focus on the middle of the distribution, the central tendency of the distribution. The population mean is a good choice there, and we can estimate it with the sample mean, provided that we have large samples, provided that we deal with outliers. We can do that in a fairly straightforward way. If you're talking about a skewed distribution, what are you talking about? Are you talking about the center of the big hump of data? Are you talking about how spread out that hump of data is? Are you talking about the spread of the tail? The focus is maybe not so obvious. As I've briefly identified, there are different techniques for dealing with this problem, and I haven't really highlighted all that clearly, but all of them have strengths and weaknesses, and indeed I'll probably try and do a supplemental lecture on them later on and talk about that in somewhat greater detail. But here again, even so, I think with skewed data from non-normal populations, it's important to look for outliers and remove them or change them if possible. Even if you have skewed data, it's still worth keeping good notes in your laboratory. And if someone has a reaction time that's like 10 seconds long, it's you probably want to remove or change that value, because that's probably a ridiculously long reaction time for the trial that you're doing. It would be better than just to do it, to look at your notes and say, oh yeah, person number 12, during that day there was a failure when the reaction time program tried to install an update, and it totally screwed up the latter series of trials in her run. And so that probably explains why she has these really long values for her reaction times. I feel comfortable now removing that data, or maybe replacing it with an average for the person's earlier trials, if that's appropriate, rather than just saying, this is clearly wrong or weird, so I'm just going to change it without a clear sense of why it's wrong or weird. And once again, and this is like the 4th or 5th time I've said it in this lecture, large samples. Large samples mitigate a lot of these problems. As bad as it is to use the mean to describe reaction times because of the skewed nature of the population, the problem's a lot less bad if you have large samples. That mean is a much better estimator of the center of the population distribution if it's drawn from a fairly large, if it's calculated from fairly large samples than it is from fairly small samples. Large samples, well recruited, solve or even prevent, in a sense, a lot of problems before they even start. Anyway, thanks for paying attention. As I always say, I appreciate the time that people take to watch these videos. If you have questions, let me know. Otherwise, just relax, make yourself a cup of tea or something like that. Take it easy. Hopefully this stuff will sink in. If it doesn't, or if you have questions, as I've already said, let me know. Bye-bye.